Okay, in the same way that pKa can be affected by delocalization of electrons, delocalization can also influence product distribution. So what I mean by that is if you have this type of structure and you add HBr to it, we could end up having a positive charge either here or here, depending on where hydrogen goes. But this is much more likely to occur because this is a benzylic carbocation. So when you look at a population of molecules, a vast majority of them are in this state. The ones that go here, if they have long enough to live, they'll move their hydrogen over, so they're going to have a hydride shift. So when bromine is looking for a place to land, it basically sees right there is where to go. So the delocalization has actually influenced the stability of the carbocation and therefore dictated where bromine is going to go. So you have to think through your mechanisms when you look at that. One note about the majority product. Major product you see listed in most organic chemistry reactions are things that could be from 60% yield to 99% yield. And every reaction is going to have its ideal set of conditions. That's something that we tend to work on in the lab. So in general, we're looking for what the major product is, and we don't get too bogged down with, at least on paper, at this level, as to which one you'll get 99% of and which one you'll get 70% of. When we look at isolated dienes, so these are things that have two double bonds. Remember that I'm a diene chemistry nerd joke, right? You all have seen that t-shirt. Well, diene means two ene bonds, so two double bonds. If you add one equivalent of HBr, you get one of those ene bonds or alkenes to react with bromine. If you have a lot of excess stuff, then both of them will react. Again, they go Markovnikov fashion to the most substituted carbon because of the fact that this is a carbocation type of intermediate. These two dienes, or two ene bonds, do not work in conjunction with each other. They're completely independent of each other, and that's sort of where we get our product from. Okay? Electronically, they're not totally independent from each other, but you get my drift. The alternative type of system is when you have a conjugated system. So usually we talk about that as a double bond, single bond, double bond, that type of thing. They're special because other stuff can happen to them. So let's first look at the most direct path to products here. Here we have a diene that we're adding HBr to. Let's say that that goes ahead and attacks over here. Your hydrogen would go here, leaving a positive charge right there. Bromine comes in, attacks that positive charge, and bam, you end up with a product. We refer to this product as a 1,2 addition product because the hydrogen was on the first carbon, 1, and the bromine ends up on the next carbon, which would be 1, 2. So it's on two carbons next to each other. That would be number 1, that would be number 2. However, because this is a conjugated system, this guy can be stabilized through, you guessed it, resonance. So these electrons can actually move right here, and when it does that, you end up with a positive charge right there, and bromine could see it if it's right here and go attach right there. Well, that means that hydrogen would be here and bromine would be here. That would be a 1, 2, 3, 4 carbons apart where the hydrogen and the bromine are attached. So that's a 1,4 addition product. Note that this double bond right here is actually in a different location than where we started. It's actually in between where the double bonds were in the beginning of the reaction. And so you definitely know that something's happening in that particular case. Now, when you start looking at an asymmetric diene, we can have different possibilities that happen. Let's say that this guy were to come and grab your hydrogen. So we're going to look at this double bond reacting first. If that were to happen, you could end up with a secondary carbocation right there because your hydrogen went right there. And through resonance, you would end up with another one that would be a tertiary carbocation. If, on the other hand, this double bond reacted, you would first make a secondary carbocation that could then go through resonance, and guess what? It forms a primary carbocation, which is not nearly as stable as a tertiary carbocation. That is why the energy required for this guy to react, or the most substituted alkene bond to react, is higher than it is for the less substituted alkene. Okay? So if we're looking at what the products look like in an asymmetric conjugated system, we would first make this carbocation. Bromine sees, oh, where do I go? I go straight to the carbocation, and we end up with a 1,2 product. Again, this can resonate, moving your positive charge down at this guy. Bromine comes over and attaches right here, making a 1,4 product. Just show you that one more time. So hydrogen would be right there, hydrogen would be right there, 1 carbon, 2 carbons, hydrogen, bromine. Following that down, we've got hydrogen right there, hydrogen right there, on the 1, 2, 3, 4 position. So this would be the 1,4 product. I had to splice some pages together here to make sure I was totally on the right page, but okay, you can somewhat control a reaction by just changing the reaction conditions. And before I confuse you with too much information, let's look right here. Going back to our original reaction, we've got a symmetric diene. HBr adds to here, adds to here. Okay? Well, we call this 1,2 product the kinetic product. The 1,4 product, at least in this case, and is quite often, the thermodynamic product. Not always. I'll come back and talk about that in just a minute. But let's assume right now that that's what we got. That's what we got. Well, if you look at the energy level diagram, there's some interesting stuff that happens. Okay, I'm going to go back and look at my original mechanism here. Notice that no matter where I get my 1,2 or 1,4 product, the first thing that happens in both cases is I make this carbocation. That actually takes quite a bit of energy because it's a positive charge out of nowhere. And so that's going to be your biggest energy hump, if you will. They create the same intermediate, which is represented by this point right here. You then have two alternatives. You could either go directly to this guy, which you see right here. Okay. The other alternative is to first rotate bonds, or flip bonds rather, form the other resonance structure. That takes energy. So if it's going to take energy, then that means I need to reflect that in the energy level diagram. So it's going to take more energy in this case. But I said it's a thermodynamic product. Well, what thermodynamic product means is that it's an overall lower energy product. So it's going to take more energy, but it's going to make more energy. Okay? So it's a lower overall energy state for the thermodynamic product than it is for the kinetic product. The reason why this is the thermodynamic product is that if you recall when we talked about alkenes, more substituted alkenes are more stable. This guy has one substituent in both of its alkene carbons, so sp2 carbons. Here we have one substituent this direction, one substituent this direction. There's more substituents around our alkene bond, and therefore it's more stable. That's why it's a lower energy state. But again, you have to put in energy to make more energy in the end. So we can actually control this reaction, at least in large part, just solely based on temperature. Because the kinetic product, basically what you're trying to get the kinetic product to do is, okay, make the carbocation and react really fast. And this never happens. Well, that means that you've got to lower the temperature. And I mean really low, like -78 type of thing. Thermodynamic products, on the other hand, if you give them a little bit of energy, they can go, ooh, I can go uphill, so then I can come back down. So they need just a little bit higher temperature, often run at 0 degrees, a little bit higher maybe if you want to get dangerous. And so they have a little bit extra energy to go up that extra barrier. Okay. When we talk about the kinetic product, we often talk about kinetic or proximity effects, but basically what that means is that, hey, my hydrogen left off over here. The bromine's kind of floating around in the water right here. Not water, but you get what I mean, water, in a liquid. And so bromine would be right there and say, hey, I'm just going to attach really, really fast. Proximity effect tends to help the 1,2 addition occur. So don't get confused with that terminology. My big point there. How can you tell which one's the kinetically favored product and which one's the thermodynamic product? Well, it's actually a little bit easier than what you might think. The kinetically favored product is the 1,2 product. So it's the one that's going to have a short carbocation lifetime. The nucleophile is going to get onto that positive charge really, really quickly. The thermodynamically favored product can be the 1,4 or the 1,2 product. It's usually the 1,4, but not always. So we have to look at the two options. So in this case, as I said, we have two substituents around that alkene, and here we only have one. So let's go back to our asymmetric diene example. In this case, here's our 1,2 product. My apologies, I did not draw that in earlier. And here's our 1,4 product. Well, actually, when you look at it, this would be my kinetic product, and this is actually the thermodynamic product also, because we've got 1, 2, 3 substituents around this guy, and here we only have 1, 2. That's no. So this is both the kinetic and the thermodynamic product, which means that you don't really have any differentiation when it comes to the energy level diagram product, at least in this state. Okay. Hope everybody enjoyed that. On to the next.